Ever look at a skyscraper and just wonder, how does that not fall over? Well, in this explainer, we're going to peel back the curtain on the invisible physics that really keeps our whole world from tipping over.
It all comes down to one single fundamental idea: balance. But to really, really get it, we've got to start small, like infinitely small.
All right, section 1, the still point. To figure out how massive objects stay put, we first need to shrink the entire world down to its absolute simplest form.
So to do this, physicists use this awesome concept called a point mass, or, as it sounds in Italian, a punto materiale. Just picture a tiny, single speck of dust floating in a sunbeam. It's got a location, sure, but for what we're doing, it has no size, no shape, 0 dimensions. And that is our perfect starting block. It's where the rules of balance begin.
Okay, so for this little dot to be in what we call equilibrium, which is just a fancy word for being perfectly still, there's one super simple rule. You just find all the pushes and pulls acting on it, and if you add them all up and they cancel each other out, the total force is 0. The point doesn't move. It's really that simple. That's all well and good for a tiny theoretical dot, right? But what about a book? Or a chair, or, well, you. The real world is made of things that actually have dimensions. And that changes everything. Section 2, beyond the point. Let's see what happens when we scale up from our imaginary dot to the actual solid things we see and touch every day. Physicists have a name for this too, a rigid body, or corpo rigido. Now, it's an ideal. Think of a steel beam that just won't bend, or a diamond that won't flex no matter what you do to it. The key thing here is that by adding size and shape, we've just added this fascinating new wrinkle to the whole puzzle of balance. So here's where it gets really interesting. Even if all the forces on one of these rigid bodies add up to 0, it's not guaranteed to be still. Not at all. It can still spin. So if we want to figure out how to stop something from spinning, it makes sense that we first have to ask, what makes it spin to begin with? It turns out it's not just about how hard you push. The answer is a concept called torque, or momento di una forza. Now, don't let the fancy name scare you, because you use it literally every single day. It's that twisting power you use to turn a doorknob or open a jar of pickles. See? It's not just about pushing, it's about twisting. Okay, so for anything to twist or turn, it has to have a pivot point. In physics, we call this the asse di rotazione, the axis of rotation. The best example? A door. It can't just float around, it's stuck on its hinges, right? Well, that line of hinges, that's its axis of rotation. The whole door has to swing around that one fixed line. And right here, this is the secret sauce. The lever arm, or braccio. It's simply the distance from that pivot point, the hinge, to where you're actually pushing. Think about it. If you push a door right next to the hinge, it's tough to get it to move. But if you push way out at the edge, by the handle, it swings open easy. That's because you have way more torque. This incredible relationship between how far away you are and how much force you create, it gives us one of the oldest, most powerful tools humanity ever came up with. The lever. So a lever is just any rigid body. Could be a giant crowbar, could be a tiny pair of tweezers that we are cleverly using to control torque. We're using it to manipulate that twist. You could almost call it a torque machine. And this shows perfectly how we can play with this idea. With an advantageous lever, like a crowbar, you put in a little bit of effort on a long arm, and you get a huge force on the other end. But then look at a disadvantageous lever, like tweezers. We do the exact opposite. We put in a lot of force with our fingers to get a tiny, super precise movement at the tip. We're trading all that force for pinpoint control. Okay, so we know that for an object to be still, all the forces have to cancel out. And now we know all the torques, all the twists have to cancel out too. With these two rules in our pocket, we can finally understand the different kinds of balance we see all around us. It all comes together at one single, super important spot inside every object. Its center of gravity, or barycentro. It's a theoretical point, yeah, but you can basically think of it as the average location of all of an object's weight.
If you could actually balance a whole object on just one fingertip, you'd have to put your finger right under this exact spot. When it comes to balance, this point is everything.
An object's stability completely depends on this point. In stable equilibrium, the center of gravity is as low as it can possibly be. So if you nudge a pyramid, its center of gravity has to go up, and gravity just pulls it right back down. Simple. In unstable equilibrium, like a pencil balanced on its tip, the center of gravity is way up high. Any tiny nudge makes it lower, so it topples over. And then you have indifferent equilibrium, like a ball on a flat floor. When you roll it, the height of its center of gravity doesn't change at all, so it's perfectly happy to just stay wherever you leave it.
So there you have it. From a tightrope walker to a towering skyscraper, it's all just this beautiful, elegant dance between forces, twists, and the center of gravity. You get the fundamental principles now. So the real question is, now that you can see these invisible forces at play all around you, what are you going to do with it?